Welcome. Today we're diving into the fascinating world of large language models, or LLMs. These powerful AI systems are transforming the way we interact with technology, enabling everything from smart chatbots to advanced text generation. But how do they actually work? At the core of their magic are two essential concepts: tokenization and embeddings. In this video, we'll break down these ideas step by step, making them easy to understand even if you're new to the field. Let's start by exploring what LLMs are and why they matter in today's digital landscape. Understand LLMs, we first need to talk about tokens. In the context of language models, a token is a small chunk of text. It could be as short as a single character, like a, or as long as a whole word, like apple. The model doesn't see text the way humans do, it sees a sequence of these tokens. By breaking down sentences into tokens, LLMs can process and analyze language in a structured way. This is the first step before any deeper understanding or generation of text can happen. Tokenization is the process of splitting text into tokens. Imagine you have the sentence, "The cat sat on the mat." Tokenization breaks this down into individual pieces. The cat sat on the mat, and sometimes even punctuation marks. This step is crucial because it allows the model to handle language in manageable parts. Different models use different tokenization strategies, but the goal is always the same: to convert raw text into a format the model can work with. There are several ways to tokenize text. Some models use word-level tokenization, splitting text by spaces. Others use subword or character-level tokenization, breaking words into even smaller pieces. For example, the word unhappiness might be split into un, happy, and ness. This flexibility helps LLMs handle new or rare words more effectively, making them more robust in understanding language. Tokenization isn't just a technical detail, it's fundamental to how language models work. By breaking text into tokens, LLMs can process language in a way that computers understand. This step also helps models deal with different languages, slang, and even typos. Without tokenization, it would be nearly impossible for LLMs to analyze and generate human-like text. Once text is tokenized, each token is mapped to a unique number. This is called numerical encoding. Computers can't process words directly, they need numbers, so every token gets its own ID and a vocabulary list. For example, cat might be 102 and sat might be 205. This numerical representation is the bridge between language and computation. Now let's talk about embeddings. After tokens are converted to numbers, they're transformed into embeddings, dense vectors of numbers that capture the meaning of each token. Think of embeddings as a way for the model to understand relationships between words. For example, the words king and queen will have similar embeddings reflecting their related meanings. Embeddings are like coordinates in a high-dimensional space. Each token is represented as a point in this space, and the distance between points reflects how similar the tokens are. For example, cat and dog will be closer together than cat and car. This spatial arrangement helps the model understand context and meaning, which is crucial for generating coherent text. Embeddings aren't just assigned randomly, they're learned during training. As the model processes massive amounts of text, it adjusts the embeddings to better capture the relationships between words. Over time, this learning process helps the model develop a nuanced understanding of language, including synonyms, analogies, and even cultural references. Let's see embeddings in action. When you ask a language model a question, it converts your input into tokens, maps them to embeddings, and then uses these embeddings to find patterns and generate a response. This process happens in milliseconds, allowing for real-time conversations and smart text generation. Modern LLMs use contextual embeddings, which means the meaning of a word changes depending on its context. For example, the word bank has different meanings in river bank and bank account. The model's embeddings capture these subtle differences, enabling more accurate understanding and generation of text. Embeddings are the backbone of language understanding in LLMs. They allow the model to capture complex relationships between words, phrases, and even entire sentences. This deep understanding is what makes LLMs so powerful, enabling them to generate text that feels natural and relevant. Once the model has embeddings for each token, it uses them to make predictions. For example, given the phrase, "the cat sat on the model predicts the next word by analyzing the embeddings and their relationships. This prediction process is at the heart of how LLMs generate text. LLMs are built on neural networks, complex mathematical structures inspired by the human brain. These networks process embeddings through multiple layers, each layer extracting deeper features and patterns. This layered approach allows LLMs to handle everything from basic grammar to advanced reasoning. A key innovation in LLMs is the attention mechanism. This allows the model to focus on the most relevant parts of the input when making predictions. For example, when answering a question, the model can attend to the specific words that matter most, improving accuracy and coherence. Most modern LLMs use a transformer architecture. Transformers are designed to handle sequences of data, like sentences, by applying attention mechanisms across all tokens. This architecture is highly efficient and scalable, making it possible to train massive models on huge datasets. Training a large language model involves feeding it vast amounts of text data. The model learns to predict the next token in a sequence, gradually improving its understanding of language. This training process can take weeks or even months, requiring powerful computers and lots of data. After initial training, LLMs can be fine-tuned on specific tasks or domains. For example, a model might be fine-tuned to answer medical questions or write legal documents. Fine-tuning adjusts the embeddings and model weights, making the LLM more specialized and accurate for particular applications. Once trained, LLMs are ready for inference, that is, using the model to generate or analyze text. When you type a prompt, the model tokenizes your input, converts it to embeddings, and then predicts the most likely next tokens. This process is what powers chatbots, translators, and many other AI applications. LLMs are used in a wide range of applications, from virtual assistants and customer support to content creation and language translation. Their ability to understand and generate human-like text makes them incredibly versatile and valuable across industries. Tokenization isn't always straightforward. Different languages, slang, and creative writing can make it tricky to split text accurately. Models must be carefully designed to handle these challenges, ensuring that tokenization doesn't lose important meaning or context. While embeddings are powerful, they're not perfect. Sometimes subtle meanings or cultural nuances can be lost. Researchers are constantly working to improve embeddings, making them more sensitive to context and meaning, especially for underrepresented languages and topics. One challenge in tokenization is dealing with words the model hasn't seen before. These are called out-of-vocabulary words. Subword tokenization helps by breaking unfamiliar words into smaller, known pieces, allowing the model to handle new language more flexibly. LLMs are often trained on multiple languages, requiring tokenization strategies that work across linguistic boundaries. Multilingual tokenization allows the model to process and understand text in many languages, making LLMs globally useful. Embeddings aren't just for individual words, they can represent entire sentences or paragraphs. Sentence embeddings capture the overall meaning of a phrase, enabling LLMs to compare and analyze longer pieces of text effectively. Thanks to embeddings, LLMs can perform semantic search, finding information based on meaning, not just keywords. For example, searching for how to bake bread will return relevant results even if the exact words aren't used because the model understands the underlying intent. Embeddings allow LLMs to measure how similar two pieces of text are. This is useful for tasks like plagiarism detection, duplicate removal, and recommendation systems. By comparing embeddings, the model can quickly identify related content. LLMs can perform zero-shot learning, meaning they can handle tasks they weren't explicitly trained for. Thanks to rich embeddings, the model can generalize from its training data to new situations, making it highly adaptable. Transfer learning is another advantage of LLMs. The knowledge gained from one task can be applied to another thanks to shared embeddings and model architecture. This makes LLMs efficient and effective across a wide range of applications. Embeddings can be used to personalize user experiences. By analyzing user input and preferences, LLMs can tailor responses, recommendations, and content to individual needs, creating more engaging and relevant interactions. With great power comes great responsibility. LLMs must be used ethically, especially when handling sensitive data or generating content. Developers need to be aware of potential biases in tokenization and embeddings and work to ensure fairness and transparency. Tokenization can introduce bias if certain words or phrases are split in ways that disadvantage particular groups or languages. Careful design and testing are needed to minimize these biases and ensure that LLMs treat all users fairly. Embeddings can also reflect biases present in training data. If the data contains stereotypes or imbalances, the model's embeddings may reinforce these issues. Ongoing research aims to detect and reduce bias, making LLMs more equitable. Researchers are constantly improving tokenization methods. New algorithms aim to handle more languages, dialects, and writing styles, making LLMs even more versatile and accessible to users around the world. Embeddings are also evolving. New techniques like contextual and dynamic embeddings allow models to capture even richer meanings and relationships, pushing the boundaries of what LLMs can achieve. Visualizing embeddings can help us understand how LLMs organize language. By projecting high-dimensional embeddings into 2 or 3 dimensions, researchers can spot clusters of similar words and gain insights into the model's understanding. In real-world applications, tokenization must be fast and efficient. Whether processing a tweet or a novel, the model needs to split text into tokens quickly, ensuring smooth and responsive user experiences. Recommendation systems use embeddings to match users with content they'll enjoy. By comparing user preferences and content embeddings, these systems can suggest articles, videos, or products that are most relevant to each individual. Chatbots rely on tokenization to understand and respond to user messages. By breaking down input into tokens, the model can interpret intent and generate appropriate replies, making conversations feel natural and intuitive. Language translation models use embeddings to map words and phrases between languages. By understanding the meaning behind the text, these models can produce accurate and fluent translations, bridging communication gaps worldwide. Summarization models use tokenization to break down long documents into manageable pieces. By analyzing tokens and their relationships, the model can generate concise summaries that capture the main points of the original text. Sentiment analysis models use embeddings to detect emotions and opinions in text. By capturing subtle cues in language, these models can determine whether a message is positive, negative, or neutral, helping businesses understand customer feedback. The future of tokenization is bright. As models become more advanced, tokenization methods will continue to evolve, enabling even more accurate and flexible language understanding across diverse applications and languages. Embeddings will also keep improving, capturing deeper meanings and more complex relationships. As research progresses, we can expect LLMs to become even better at understanding and generating human language, opening up new possibilities for AI. Wrap up: tokenization and embeddings are the foundation of how large language models work. By breaking text into tokens and representing them as embeddings, LLMs can understand, analyze, and generate language with remarkable accuracy. As these technologies continue to evolve, they'll play an even bigger role in shaping the future of communication, technology, and society. Thanks for joining us on this journey into the heart of LLMs.